This video is about 2gen type 1. I will derive a 41 move algorithm and then I will derive a 35. This type of 2gen involves inner slice R and outer face U turns only. That type of moveset, and I have that here. So let me begin by deriving a few key components. I will do this for each of the other types of 2gen as well. I will start off with a few basic move sequences that we observe either by move repetition or just by playing around with the cube. These are probably the most obvious short move sequences that one can find if it's not by repetition, for example. For this type, first of all, let's talk about Pll Parity. If we know Chris Hardwick's 6-move Pll Parity algorithm for switching two opposite dedges, that is R2, U2, R2, UW2, R2, lowercase u2. Again, this tutorial is going to be in Old WCA notation. We can rewrite this as R2, U2, R2, U2, R2, and then R2, lowercase u2, R2, lowercase u2. These are equivalent. Quick way to check is both of these move sequences are in here, and we know that if we apply Pll Parity twice, then it will cancel itself out. So in other words, we will have a solved cube, and we do. Let me switch now to the 4x4 supercube. After we execute Chris Hardwick's algorithm, we see that some of the arrows are not correct on these, but in a solved cube, they are all facing this direction. Similarly here, if I remove that now, and I remove this piece, this is very important. This type of Pll Parity is, some people might call it non-pure, whatever you want to call it or think of it as, that's fine, but there's two things it does. Don't ignore this. These four centers right here, do not ignore that. It takes this one by center block and it switches it with this one by 2 center block. Or in other words, you can think of it as rotating this composite center 180 degrees. That's very, very important for 2gen. Very, very important. And why I'm saying 2gen is this is all in this moveset. All of these moves are in this moveset, lowercase ru. This is considered a 2gen algorithm. In addition, of course, it will also switch this one by 2 center block with this one. Now, separately, this piece right here well, it does something to these centers, but maybe you guessed that once you have this, applying this move sequence here is going to solve these two, or at least switch them so that this face is not discolored anymore, that all the centers in here are orange and all the centers in here are red. And it does. And lastly, this move cancels with this one, and these two moves right here merge as a wide turn of U. So that's why Chris Hardwick's algorithm works the way it does. So the first move sequence, I'm going to write it here, that we need to remember is that one. Pretty straightforward, I would think. Another move sequence that we need to also look at, if you just mess around with the cube a little bit, if you do R, U2, R, U2, R prime, U2, R prime, U2, this is another one. And the reason why I'm mentioning this is because, look, it switches the centers in the same way that Pll Parity, I'll just call this Pll Parity, okay? Pll Parity does. That's going to be important for the 35 move sequence that I'm going to show in this video. But that will come later, but I'm just going to keep that move sequence here. And it also does something here. Take a look at this. This 1 by 3 block and this 1 by 3 block. Looks very familiar with, for example, if we would go to the standard algorithm, for example. If you see my derivation video of the standard algorithm, then you've seen the commutator U2 left, U2 R prime, U2 R, U2 L prime. That's 3 1 by 3 blocks here in this fashion. And the reason why this works is because it's a piece isolating commutator. For example, if I delete this U2, and I delete this, and I just have L U2 R prime, well, you can't really see it, but if I do a U2, then you probably can see it. We have a 1 by 3 block isolated in the U face. Let this be our x and a piece isolating commutator xy. Then our y will be a U2 move to put an alternate 1x1x3 block into that location. Then we will undo this first piece, or algorithm x, with its inverse, and then we will also undo y to complete the piece isolating commutator. When I apply it to the cube, then we have three 1x1x3 blocks cycled in this fashion. Of course, for the standard algorithm, all I would have to do is a shift, or a cyclic shift. And on the 4x4 Parity Algorithms page at Speed Solving Wiki, if we go to pure flips, single parity, under one dedge flip, and under shortest half-turn move algorithms, I talk about cyclic shifting right here. Basically, it means that we are going to take the first move and make it the last move, or take the last move and make it the first move. And you can do this any number of times. So I might say in the future, we're going to shift it 3 moves, or shift it 4 moves, or something like that. That's what this means. So if we shift it 1 move, then we have this exact same commutator that I just showed you for the standard algorithm, because if I write this on one line, 2 of these U2s cancel with each other, and then we're left with this, which is exactly the same commutator as the standard algorithm. Another type of piece isolating commutator of 1x1x3 blocks, besides using LU2 R prime for our x, is F prime R prime F, for example. And that will isolate this 1x1x3 block in the U face, as you can see there. And it also isolates one in the D face. So quickly, let me just do like U2. And with the commutator, we can abbreviate the commutator x, y, x prime, y prime, or some people might think of x inverse, y inverse as x comma y in brackets like this. And this software, Cube Twister, has this implemented inside of it. So I'm just going to take this like that in this software. And we have the same exact 3 cycle of 1x1x3 blocks as the standard algorithm, but it's a different type of algorithm with fewer quarter turns. But I mentioned that we can also do D2, so if I just made that a D2, then we have a different type. If I just cyclically shift this 4 moves, just cut and paste. Then this 3 cycle of 1x1x3 blocks is in the M layer, as I call it, the M layer. Just as a brief review, for those who haven't seen the derivation of the standard algorithm, or who just want to see a quick derivation of it, if I just use the 3 cycle of 1x1x3 blocks for the standard algorithm, I can just briefly show you the general idea for making parity algorithms. Once I have this, I basically want to get all of these 1x1x3 blocks in the same slice. I see that I have one here, I move it down, and then I move this over. Now they're all in the same slice. I do a quarter turn to solve back half of the centers and half of the wing edges, and then I just undo the moves that I did beforehand. This looks familiar. Now I can do some outer setup moves. If I do a B2, and I undo that with B2, then I can see that this wing edge, if I just do an R2 move, will be there, and this 1x2 center block, which is not affected, will be moved down here to where this black 1x2 center block moves, so black will swap with black. So if I do R2 and then R2, then it creates such an algorithm. So that's the idea. For those who haven't seen the derivation of Lucas parity, or the derivation of another edge flip algorithm, I believe it's called, some people might know it as Waffles algorithm. This is the beginning of the restriction that will lead us into 2gen. If I wanted to have an algorithm which only uses U2 phase turns, puts an extra constraint on us, I can do the same exact thing as I did before if I just start with an R prime and then undo with R setup move. Basically how I know to do that is I want these two 1x1x3 blocks to move down. If I want them to move down, I need the last move to be an R prime, because the inverse of the setup move is the direction they're actually going to move. But in order to do that, I need to first do the setup move R, because that is the inverse of this. So that's why I know to start with R instead of R prime when I want to move them down. That's just a general procedure, which I will assume that you will know from now on in this video series for conjugation or setup moves. Oh, and silly me, I went in the wrong direction. I don't want them to move towards me, I want them to move away from me. To move away from me, that's the move R. So the inverse of the setup move must be R, therefore the setup must be R prime. Okay, so now they're in the bottom of the R slice, this is in the top, and therefore with a U2 setup move, I do that U2 setup move, now it is also in the R slice. From that point I can do a quarter turn, and I have a different case here. Now to mimic the standard algorithm setup, even though this is not what should be ideal or even possible to use for this type of restriction, is to do a U2 setup move to this. Then this will make this 1x1x4 block separate from this 1x2 block. That with a, I want this to move down, so I want it to move towards me, so R prime, so the setup move must be R. I'll put these on one line. And this looks identical to that, but we're not going to do that for this. Instead, this is what we are going to do. These are the setup moves. We will be doing R and R prime. I want this to move towards me once. And now what I want to do is separate this single wing edge QB from the rest with a U2 setup move. And I'm going to undo that setup move. And then I will be doing an R2 to make it a single dedge flip prematurely before the centers are fixed. It turns out that now that I have this, if I do the following setup moves and I undo them, and it looks like I didn't change anything, but I'm recording moves. You can do that with Cube Twister, and thus you can see the moves here that I did add some moves. And they enabled me to still preserve this dedge that was flipped previously, but now it won't discolor any centers. More specifically, this black 1x2 center block is switched with this one. So if we go back here and I undo these setup moves, originally this overall algorithm piece switches this 1x2 center block with this one. Now if we observe the setup moves without that piece on the cube itself, we can see that it puts two black or same color 1x2 center blocks in those two locations. And now imagine if we do these setup moves before we do the entire algorithm, then that is going to enable us to switch same color centerpieces with each other, or in other words, not discolor any centerpieces at all. Also, these setup moves do not break up the pairing of the dedge that was here, nor do they put another dedge in this location where the original one was. I just undo them. We still have a black and orange dedge in this location here. So therefore you can observe that when I have a setup like this, I can do those setup moves, and I can undo those setup moves to get this. And that is something that we will probably see in some of the algorithms that I derive in this 2gen tutorial. So again, this is just an additional restriction. This is the bridge between the standard algorithm and 2gen. So now we're ready to start 2gen. We will keep these two move sequences that I mentioned before on hand. With this first type of 2gen, it's going to be 41 moves. As I mentioned in the intro video, the move optimal solutions for this type of 2gen is 22 moves, and I'm going to be showing you how to derive one which is 41. But I will also show you how to derive a 35 by hand, which is still a lot more than the optimal. However, these are pretty easy to understand. Just as with the previous approach where we want to isolate a 1x1x3 block in some face, such as in the U face, with this type of 2gen, the first type of algorithm that I'm going to show you, is going to isolate it in the R slice. You think of it not as the U face, as U is going to be RY in piece isolating commutator XY, but R will be Y in our piece isolating commutator XY. That's the key thing. To start off with, let me just do R prime, U2, R, U2. This is a commutator, basic move sequence. If we have to switch two centers, for example, like this, when doing reduction, we see that this center is in line with this one, so therefore we can just do these moves and then we switch them. That's pretty much the idea of this type of move sequence, so it shouldn't be anything foreign. So we start off with R prime, and you can go with R as well, but that would make this derivation longer because what I would have to do is mirror it about M and rotate it about the Y axis, or in other words, inverting all of the R moves, and what you'll see soon is U turns as well. But I'll start with R prime. I'm going to do U2, R, U2. From this point, if I just do the move R prime, then I have a dedge here that's paired. And this kind of tempts me to do Pll parity when I see it. I'm like, whoa, look at that. And when I do recall that Pll parity, well, let's take a look at it real quick. And this is what I call Pll parity. It just goes centers, but see this center here rotates at 180 degrees. But at the same time, this algorithm has that rotated 180 degrees. So this Pll parity, and when we apply it, is going to solve back that center for the supercube. The supercube matters for 2gen. What happens when the centers on the supercube does matter. And later on, for some of the other types of 2gen, we're going to be looking at the decompositions of the moves here in cycles for different pieces, and I'll explain that as I need to. But for right now, I apply Pll parity to this. It's going to basically correct this 2 by 1 by 3 block. It's going to rotate 180 degrees and put it here. In addition, it's going to take this 1 by 2 center block and put it back where it belongs. It's going to move this one here. So this is going to be yellow, as you can see. The idea is I want to solve back as many pieces as possible because I want to be able to isolate a piece in a slice or face as easily as possible. The way you can isolate it easiest is if there are fewer pieces affected by the current algorithm. The fewer the better. Now this right here is a special type of move sequence as well. It's a cyclic shift of something very, very special. As we can see here, it's a 4 cycle of wing edges and a 2-2 cycle of centers or X centers. A 2-2 cycle means that 2 times 2 equals 4 pieces affected. 1, 2, 3, 4 X centers. And clearly there are 4 edges affected as well. If I take this, I'm going to temporarily paste it here because I'm going to do a little bit of arithmetic with it. I just take this and merge these as an R move. And then I shift this over like this so these become an R move. And now I take this move and I shift that there, and then I break this up as 2 R's. I still have the same cycle type here for both types of pieces because I didn't change the algorithm. All I'm doing is conjugating it. Shifting means you conjugate. When I take this move R and I move it to the front, it's the same as if I do the set of move R and invert it with R prime because these 2 R's cancel. Now this right here is a very popular sequence that's well known. Basically, it's R, U2 repeated 4 times and then R at the end. That's a compressed way to write it. Very popular algorithm. So for those who know that algorithm, this is basically using that to create a 2gen algorithm. So even though I'm not going to use this anymore in this format, I'm just going to paste that here because it's useful. I'm going to resume back to this cyclic shift of that, which we will be using. Now the reason why is it's obvious, a 1 by 1 by 3 block here. If I could aim to isolate that in the R slice, I could try to isolate in the U face, but as you will see with some experimentation, it's really not possible to do that. but it is possible to isolate in the R slice with very few setup moves. So for one, this is the setup move route that I took. If I do, for example, U prime and undo it with U, and then I want to pretty much get this 1x1x3 block into the top face with this, and then do a U2 of this to get all of that into the left half of the cube. And all that will remain is this 1x1x3 block in the right half, and specifically in the R slice. So if I move it up, which means I move this slice away from us, or R, I have to start out with R prime. And now I can do a U2. I have to do a U2, not a U. I need to get this completely out of this right half of the cube. And there you go. This 1x1x3 block is isolated in the R slice. So from this point, what do you think we do? Let this algorithm piece be X in our piece isolating commutator XY. So I'll write a brackets, and let Y be equal to the move R in our piece isolating commutator XY. Then I have this right here, which looks very familiar from what I showed you earlier with that restricted move algorithm with L and R and U turns only. From this point, I can just simply do manually do a U2 setup move, undo that U2 setup move, that they're all in the R slice. From that point, I'll do a quarter turn. I guess I can put that quarter turn in parentheses just to help you visualize what the quarter turn is. From this point, I'm going to separate the single wing edge QE from the rest with another U2 setup move. And notice that these two U2s are going to cancel with each other, so it's pretty nice. We'll have fewer moves. And then I'm going to do the same exact setup moves pretty much as I showed before. So I will do an R2, and then I'm going to undo it with an R2. And then from this point, I'll finish off with R, U2, R prime. I'm going to undo that, R, U2, R prime. And there we have it, a single dedge flip. 47 moves, but it's uncancelled and this isn't expanded. But I wrote a program to quickly do this for us in Mathematica. I'll just paste it here. And bam. 6141 move sequence. So I'll replace this with this to make sure my program did the simplifications correctly, and it did. So this is 41 moves. Now I will go on to deriving a 35 move algorithm with this type of 2gen, using this move sequence and this one, which I mentioned previously. We already used this one, and as you'll see in the last type of 2gen that I'll be talking about in this video series, Pll Parity is going to play a key part there as well. So for this 35 move one, we start out with Pll Parity. And as I mentioned before with this algorithm, it rotates this 180 degrees as well, just like Pll Parity does. But importantly, it creates these 1x1x3 blocks, very similar site to what we just did, correct? But this time we don't have to create that or isolate that. It's already created or isolated for us. So if we simply combine this with Pll Parity, then we will have a means to create another 2gen algorithm. If I add in Pll Parity to this, then it will correct this center. And then we will be able to isolate a 1x1x3 block somehow in some way. It's a little different. It's not so much isolating. This is a little bit different. That's why I had the 41 move example first, because that literally shows a piece isolating commutator just like those, like for the standard algorithm and for Waffle's single dedge flip algorithm, which only consists of U2, face turns, and L and R moves. This one's a little bit different, but just a little bit different. Now it doesn't matter if I apply Pll Parity before or after this, because you can see the cube like this. Now if I move Pll Parity beforehand, yes, it does look a little bit different, but at the same time we still have a 1x1x3 block there, so it's not too much different. And look at this, we're going to be able to have a move cancellation here. So it's smart to do it in this order so that we can have a shorter algorithm with no effort. Because the top looks the same, and that's what matters the most, is the top pretty much looks the same. If I just revert that, you see the top is identical. What I'll do is I'll write these on two separate lines for simplicity. Just like with the previous algorithm, I can do a quarter face of a U move. It's ideal to use quarter turns of U moves. It could be possible to find a 2-gen that consists only of U2 face turn moves and R moves, and R prime and R2, but I don't know. I never really looked into that, but if so, it would probably be pretty long, if it is possible at all. From that point, since the R slice is what is affected, it might be a little bit unobvious, but let this algorithm piece be X in our commutator XY. And I'm not going to say piece isolating commutator, even though it's sort of similar, it's still not what I would consider a piece isolating commutator. Let that be X in our commutator XY, and let R2 be Y. R2 be Y. Now we have this, a whole bunch of disjoint 1x1x3 blocks in the R slice. What a mess. But we haven't applied our quarter turn yet. What will happen if we do? If we apply our quarter turn, let's say R, then we have a setup like this, where we have a 2-cycle of wing edges and a 2-cycle of 1x2x2 blocks. It may not be obvious, but in 2-gen you're allowed to do something really neat. With this, it would be kind of cumbersome to try to find setup moves that will actually make this possible to do. But maybe I could try. I could do like a U and then a U prime. And then I could do a, I don't know. If I move this, I want this to move up, I have to do R prime to have it move up. Yeah, it's a little bit messy. If I do U2 now, to get it all in the left half of the cube, and then I do, yeah, this is just not a good idea. But with 2-gen, you also can do this. Instead of a commutator, I can still use that first piece, but I can literally repeat the same algorithm in 2-gen. What I mean by that is I have this, I copied it just now, and I write R2, and I'm going to paste it, and I'm going to write R2. Now this is a different formation. Let's see what a quarter turn does for us. And it looks like this is orange, so it needs to move here, and this is black, so this needs to move here. So if I do an R prime quarter turn, let's see what it gives us. It gives us this, which look, it looks exactly like the setup that I did earlier for Waffle's algorithm, as it's commonly known as, the algorithm which is related to the standard algorithm, but it has a different setup for the ending. All I have to do is a U2 setup move and a U2 setup move. And this is all experimentation. As you will see in this whole series, it wasn't obvious to find any of these. But I'm trying to show you how to maneuver through this type of restriction. From this point, I can just do an R prime and then R. And then I have that exact same thing. So now I do R, U2, R prime, and then R, U2, R prime at the end. So I undo that setup move, and voila. And I can also, for those who don't know, I can invert this U and U prime because it really didn't matter which way I went. And I'll show you. See, it works out just the same because right here, it doesn't matter if I do a U prime or a U, the top is going to be identical. And that's what we were trying to do, is get the pieces out of the R slice. Because I want to repeat this twice, and then an R2, and R2 involves the R slice. I wanted to get these extra wing edges out, so that all that was left with these 1x1x3 blocks in the R slice when I repeated this whole move sequence. So when I apply this, it's the same exact thing. It doesn't matter which direction you go. So technically, I'm giving you two 35 move algorithms. Now to verify those 35 move algorithms, I'm going to go to my program in Mathematica and see what it gives us. So for this one, I have this move sequence and 55, 35. But 35 is still way above 22, but it's 6 fewer than 41, so that's good. I'm just going to copy this and paste it in here to verify that it is indeed correct. And it is, and it's 35 moves. So now we will move on to the next type of 2-gen that I'm going to speak about, and that is moving triple layers of U with lowercase r.